Hi guys, so in this video what we're going to do is going to look at the concept of differentiation, what it is, and we're going to look at how it's derived from first principles. So what is differentiation? Well, I want you to think of differentiation as an equation of a slope, okay, so specifically the slope of a tangent. So you can see here what I have is I have a graph here of a function. You can see here that the slope for this particular bit here is fairly shallow, and then as we get round here it's getting steeper and steeper and steeper and steeper still at different points. So this point here, if I drew a tangent here, as you can see here, and I worked out the slope of that tangent, I'm sure you'll be happy that it's going to be different to the tangent up here. All differentiation does is give us a way, without having to draw tangents to everything and work everything out on the graphs, it gives us a mathematical way to do it, and it will work for any function. So we can find out what I call the tangent function or the differential of any function that you'll come across. Okay, so let's have a look, see how this works. So I'm going to try and get this tangent here, this first tangent. I'm just going to call it T for tangent. Okay, and what I want to know is I want to know at this particular point, what is the gradient of this tangent? Okay, I want to find out what the slope is. That's the instantaneous rate of change, i.e. how is the value of y changing with respect to the value of x. So you can see here that the value of y with respect to x is less than up here because y is increasing quicker at this particular one. So it's just a rate of change, it's just how big is something increasing, decreasing, which essentially works out to being the slope. So differentiation is just calculating slopes at particular points on a function. Okay, so if I have a look at this, we can say if I take this point here, I'm just going to call it some x value. I'll do some numbers with you later, but we're going to say that's some x value. And if I get that x value, it's going to give me some function of x, and I'll just talk you through what I mean by that now. So suppose we had y is equal to x squared. That means I can rewrite that as f of x is equal to x squared. And if I put a number in, I'm going to get an answer. So if I put x through this function, and this particular one, if I put a number through, I'm going to get, for example, 2. I'm going to get 2 squared, which is 4. So I've got to put an x value out, or an x value in, sorry, and I get some function of x coming out, which is my y value. Okay, so it does whatever happens to be. Now, it's an arbitrary number. It can be any x that I want to put through, and I'm going to get an answer, a y. Now, what I have here is I'm trying to find a slope. And in order to find a slope, I need 2 points so that I can use the slope formula. And if you remember the slope formula, which was given by m, is equal to y2 minus y1 over x2 minus x1, i.e. the change in y over the change in x, the rise over the run. We all know that. That's from junior cert coordinate geometry. So I've got my first coordinate here. And what I want is I want a second coordinate. And you see this black one up here. I've already drawn the dots down here. So I'm going to get this second coordinate. And what I'm going to say is I'm going to take this, and it's going to be a distance h from the first coordinate. So whatever this x is, I'm going to add h to it, because suppose that my x is 2, my h is 3, then my new coordinate would be 5. So we should be happy that if I want this coordinate here, I'm just going to put a little arrow there so I don't get it stuck anywhere. You can see that my coordinate now becomes x plus h, which means that my function, instead of being the function of x, is now going to be the function of this new coordinate x plus h. Okay, so this is going to be a function of x plus h. And again, just think with some numbers. So if this was x was equal to 2 here, then I put the function of 2 through whatever I have, whatever the function is, which is x squared, so 2, and then I'd have 2 squared, which is 4, so I get 2, 4. Yeah, so 2 on the x, I get 4 as the y. For this one, I'm going to say my h is 3. I'm going to move this coordinate just 3 in the x direction, so I end up with 2, which is the original coordinate, plus 3, which is 5. So that now would become 5 in terms of numbers. And that means that I now have to put the function of 2 plus 3, which is 5 through. And if I do that, I get 5 squared, which is 25 up here. Okay, so all I'm doing is, instead of using numbers, we're just using the letters x plus h. So whatever this h is, that becomes my new x coordinate. That means I have to find the function of whatever this coordinate is. Now, we have the two coordinates, which means that we can put it through our slope form, which we have here. So I'm going to label the first one, I'll do this in green, x1, y1. This is x2, y2. And we can just throw it straight through. And if we do that, we get m is equal to y2, which is f of x plus h, minus y1, which is f of x, all over x2, which is x plus h, minus x1, which is x. So just to show you again, so y2, f of x plus h, minus y1, which is there, minus f of x, all over x plus h, which is x2, there, minus x1, which is x. Okay, so that means that you can see here there's going to be m is equal to f of x plus h minus f of x, all over, the x is on the bottom will cancel, and we end up with h. So what we have so far is that our slope function is given by f of x plus h minus f of x all over h. And all we've done here is we've just used the slope formula that we've had from junior cert. Now, if you remember at the beginning, I said I'm trying to work out the tangent of this line here. And what I've done, if you think about it, I've actually calculated, I'm going to put this in yellow, I've actually calculated this slope here. And you can see they're way off, because the two coordinates I've used, you can see this x plus x, f of x, and x plus h, fx plus h here. You can see here that there to that there, that yellow line, which is what I've just worked out, I've worked out the slope of that line, because they're the 2 points I've used, is nowhere near the slope of the tangent that what I'm trying to find out here. So this isn't quite correct yet, we've got a bit of an issue. Now I can make this better by reducing this h, i.e. making the h a bit smaller. So instead of going from here to here, perhaps I could go from here to here. Okay, so let's do that. So we've got that there, I'll do it in purple. And you can see now if I do this purple line, it's better than the yellow line, but it's still not close enough to the tangent. Well, in that case, I could make it smaller still. And perhaps if I went, and I'll do it green line here, perhaps if I went to here, okay, on the actual graph, on the function. So if I do that again, it's getting closer and closer and closer. But hopefully, guys, what you'll see is that as I am making this gap smaller, this h smaller, that it's coming more and more towards the true line of the tangent. So you can see the first one, which was yellow, which was pretty awful. It's actually nowhere near the tangent. The second one there, which was considerably closer on the function, has come a lot better. The green one, which gets closer still, which is getting better and better. So what I'm trying to do is I'm trying to minimize my distance of h between these two coordinates. Now, ideally, I'd like there to be no distance between them, but there has to be some distance between two coordinates if I want to use the slope function. So this is the idea of taking a limit. I want h to get very, very, very small. I actually want it to be 0 without actually getting to 0. So I want to take the limit as h heads towards 0. I know it can't be 0 because I get division by 0 here and we're not allowed to do that. But I want it to get really, really small. I want it to be 0.000000000. You get the idea, 1. So it's as small as possible, because the smaller that I can make the gap between these two coordinates, the closer I'm going to get to the tangent. And if I take the limit as h, this gap, heads towards 0, then I'm pretty much hitting this tangent. I am hitting the tangent. Okay, so if the gap is so small, i.e. it's near enough 0, then I will have the slope of that tangent. So that's the last bit there, is my m now becomes equal to, or we take the limit, okay, as h tends towards 0 of f of x plus h minus f of x all over h. And then what we have is we change our m, well, we leave it as m stands for slope, but for the notation, what we do is we say dy dx is equal to the lim as h heads towards 0 of f of x plus h minus f of x all over h. Now what that means, dy dx is just the rate of change with y with respect to x, and that's equal to this here. Now, if we have a look at x squared, for example, and we look at the graph, here it is. Okay, so we've got x squared here. You can see y is equal to x squared, and you can see that it changes no matter what, depending on where we go from. So if this, for example, is -3, you can see that's a different slope to 2 if x was equal to 2. And once we've found our slope function, once we've found our differential, then what we do is we can start putting in values of x to tell us what the slope is at that particular point. So this is what's really, really powerful about differentiation. Instead of having to draw this and draw tangents, which is very, very difficult, you have to be very, very precise with your drawing. What we have now done is we've developed an algebraic method that we will come out with a slope function that will tell us what the slope is at any point on one of these equations. Now, we'll do this later in the course, but the dy dx for an x squared graph is equal to 2x. That means that what will happen is that I can find any x value here. If I put in whatever I want, and it'll tell me the slope at that particular point, just as I was saying a second ago. So if, for example, I want to find the slope of the tangent at -3 on a y is equal to x squared graph, I put it into my dy dx function, which is given by 2x. As I said, you'll be proving that soon enough. And all I do then is I put -3 in, I get 2 times -3, and that means that the slope of the tangent at -3 is equal to 6. Likewise for this one at 2, if I want to find out what the slope is, I put 2 in here, I get 2 times 2, and the slope is +4. Now guys, it's really, really important that you get into your head that differentiation is pretty much a slope function. It calculates slopes. Okay, so slopes of tangents, and the other way to think of it is the instantaneous rate of change at a particular point, i.e. how y is changing at a particular point with respect to x.